Hello everyone, we're going to discuss in this session about the idea of virtualization. This would involve classic definitions, the underlying key requirements, the concepts to ensure how virtualization works, as well as the most trendy topics regarding virtualization such as container-based virtualizations. Of course, we'll be looking at the issue from distributed and parallel systems point of view, and the contents presented here is by no means comprehensive. I'll be trying to give pointers to the right directions for you to search and get more information about a specific technology. So in modern computers, even with a single core all CPU, we have operating systems implemented multi-threading, to do more things at the same time. On a single core processor system, the simultaneous execution is an illusion. Supposing that each thread is running a set of instructions, and when they are at work at the same time, the CPU will rapidly switch between threads and processes, and finally it will create the illusion of parallelism. Of course, the same illusion idea can be extended to other hardware resources such as memory and monitor, or maybe other parts of the computer. This is in general called resource virtualization. So, the idea for virtualization dates back to 1970s, where the legacy softwares were to run in the next generation novel hardware. As the software was developed in connection with the underlying operating system and the hardware architecture, translation of the instruction set architectures become part of the main solution. Also, we may have more stable middlewares and application layer softwares, with the trendy and recent technologies. However, as the existing hardware and the low-level software platforms change, it becomes very hard to move or re-implement the legacy softwares to or on these platforms. For better portability, virtualization can save us writing them according to the new platform. What virtualization do is therefore to allow an interchange between different interfaces. This interface exchange can happen in different levels of computer layers. Although initially it was taught for instruction set architecture level, in other words the ISA level, in the ISA level, it can be more for those any program can use and those only operating system can call. So there are like instructions that every program can call, and there are instructions that are privileged and only operating systems can call. Other levels include system call and API levels. As you may guess, in distributed platforms, virtualization is quite useful for heterogeneous platforms running different and possibly independent applications. Lastly, we show an example of 3 ARM instances that can run on the same hardware x86 platform, again due to the idea of virtualization. So let us summarize the available interfaces provided by the computer systems. Applications use library functions to reach out to the system calls, and this is actually illustrated with this picture in the slide. Without the library interface, as you can see, these system calls would be unavailable. System calls are used by libraries to reach out to the operating system calls, which may otherwise be unavailable. This way, the applications can use the privileged instructions that can only be called by the operating system kernel. On the other hand, both applications and libraries can call general instructions without the operating system interaction. And these are shown on the right, where the application layer and library layer meet the hardware. Alright, so let's look at the realization of virtualization. Virtualization can be realized in 2 different ways. In the first way, a runtime system is developed that provides an abstract instruction set utilized by the upper layer application. The runtime environment either interprets instructions like Java runtime or emulates them. Emulation also covers system calls, so that makes it hard to perform the overall realization. In the latter, a process is virtualized. Alternatively, we can shield the original hardware completely and provide an interface for the instruction set of the same or different hardware. Important thing about this is that this interface can be offered to different programs. As a result, different operating systems can run on the same hardware platform simultaneously. The translation layer is also called as virtual machine monitor or hypervisors or hypervisors in different literature and contexts. Typical examples for it are VMware and Xen. Note that with VMMs, the virtual machine monitors, we achieve great portability and better security. This type of virtualization will now not allow any crash or security problem to spread across the entire platform due to software hardware decoupling. Alright, as we mentioned before, hypervisor or hypervisors are another name for VMMs. We've got two different types of hypervisors, type 1 and type 2. Type 1 is bare metal, type 2 hosted. Type 1 requires a management console. That's what it makes different than type 2. Well, type 1 in a nutshell is a directly installed, something that is installed on the hardware. So it's a software that's installed on the hardware. Type 2, whereas the Type 2 version has already an operating system on it, and Hypervisor is installed on top of that operating system. So as I said, Type 1 requires a management console, usually installed in a remote computer to configure the Hypervisor. Management console is also responsible for dynamic allocation of instances, virtual machines between different hypervisors, and protect against failures. Xen is an example for Type 1, by the way, and it's free. However, the management software is not free. Particularly the management console with many good features, the price climb up exponentially fast. On the other hand, Type 2 hypervisors require no management console, and hence the whole management issue is left to the host's control. Type 2 assigns resources to instances irreversibly, by the way. Hence, once the instance is up and running, host allocates the dedicated resource, hardware resource, for that instance only, even though they may not be used by that particular VM. But that's the way it is. This may be a little bit problematic, as you may lose efficiency, but that's what it is. Also, instances use host's network when in connecting the internet. If you use bridged adapter, for example, you may have your own private network close to external access. Alternatively, you can use NAT, like network address translation layer, and you can open your network to outside access in internet in particular. Note that Type 2 is typically easier. However, it comes with multiple kernels, one on top of the other, meaning that the Type 2 is more bulkier compared to Type 1. Okay, so let's talk about types of virtualization. There are three types that I'll be talking about today. The first one is full virtualization. In that type, guest operating system is completely decoupled from the underlying hardware. Guest operating system requires no modification and is not aware that it's being virtualized. The full virtualization is enabled by binary translation or operating system requests. In paravirtualization, guest operating system is modified to enable communication with the hypervisor to improve performance and efficiency. The modification in the guest operating system kernel is in the non-virtualizable instructions that are replaced with hypercalls so that it can communicate directly with the hypervisor. In the hardware virtualization, hardware features such as Intel's VTX or AMD's AMD V technologies are used to assist virtualization. And in this type of hardware, privileged and sensitive calls are set to automatically trap to the hypervisor. Therefore, there is no need for binary translation or paravirtualization. Let us also mention about some of the available and known open source tools for virtualization, particularly for Linux systems. Here I'm going to talk about KVM, QEMU, and libvirt. KVM stands for kernel-based VM, or it's a kernel module. In QEMU, in short, it stands for Quick Emulator. It's a Type 1 hypervisor, and libvirt is a library for virtualization that Linux operating system supports. So remember that hypervisor is the agent that helps you create virtual machines and creates and runs the guest machine and provides the host resources to the guest. QEMU and KVM both are able to act as hypervisors, but you will see there are a lot of differences between them. They're used together in general, However, QEMU is a little slower when it comes to system which don't have hardware virtualization. KVM helps QEMU to access hardware virtualization features on different architectures. It also adds the acceleration feature to the QEMU processes. So in short, when they're together, QEMU is the hypervisor or emulator, and KVM is the accelerating agent. And the virtualization library, libvirt, is simply a virtualization management library. The main job of this library is to manage both KVM and QEMU together. It consists of three utilities, namely an API library, a daemon, and a command line tool. And this library is quite effective, and it can manage a lot of hypervisors all together. So just a little test. We're going to be spinning up VMs. You can use also the GUI support. It's all available on web, and it's all open source. So if you just spin up VMs with two types of virt, so there are virt type. If you just install the one that with the GUI support, you will see there's a virt type. And there are two options there, one with KVM and the other with QEMU. When you look at the process IDs with these two different selections, you will realize that when we don't have KVM, we use TCG, namely the tiny code generator by the hypervisor QEMU, to do the code translation, between virtual CPUs and the physical CPUs. So remember that, the physical CPUs are physical. You can, so many different number of cores, but your virtual CPUs may be more than the number of physical cores. So there is a mapping between them. This can also happen when the hardware does not support virtualization technology, by the way. In fact, supporting virtualization by the hardware means that a kernel module such as KVM can be used to map directly a slice of physical CPU to the virtual CPU to ease the translation job. This adds speed to the process. Therefore, KVM provides the acceleration with the support of hardware, and QEMU uses it to generate virtual machines on the hardware. Therefore, we can realize that when we use QEMU and KVM together, this combination makes the hypervisor type 1. Although QEMU is itself a type 2 hypervisor. Finally, based on our knowledge, we can simply assert that QEMU does not need KVM, although it can work slow. Yet KVM definitely needs QEMU to be anything useful in virtualized Linux environments. Alright, finally I want to talk one of this trendy virtualization topic called containerization. And it's another example of virtualization technology, but this time it takes place at the operating system level, more specifically at the operating system kernel level. The real benefit of containerization is that we do not need to deploy a VM for each application and consume all the energy needlessly. Containerization was developed years ago, and the Linux support for containers was available in the mid 80s or 85, but 86. But it only became very popular recently because of microservices. They became prevalent and work at large scales. We show you both Type 2 hypervisor VMs and the containers with their corresponding stack in this picture. As you can see, containers are very, very lightweight compared to the standard virtual machines. Of course, image assumes the applications XYZ use the same operating system of the host. If this is not the case, particularly for the picture for containers, if this is not the case, then we would need a guest operating system anyway. So Linux kernel achieves containerization using namespaces, C groups, and copy on write features, the details of which now are not the scope of this presentation today, but you can just go and search and get more information. You can think of the whole file system in your computer as one single container with this support. Many containers can be created very easily, using these three features of the kernel. The main advantage of containerization is the efficient isolation. In other words, we can ship binaries with all its dependencies together, and also the application migration become way easier. than before. So overall, the name for it is called the portability. So this would otherwise be quite hard and heavy with standard virtual machines. Examples of the containers that are implemented and available open source include LXC, LXT, Rocket, and finally Docker. The Docker has been the most popular with a wide ecosystem and support on a hub and many work groups around the world. Anyway, alright, so in summary, today we talked about virtualization in general, the idea behind it, and different types of virtualizations that can be used in large-scale distributed systems. We particularly have provided open source virtualization tools that uses the enabled hardware and also to enable creation of virtual machines. And if you have any questions, please drop to my email box down below, and I'll be glad to answer your questions.